Take it away, Isaac.
Oh, okay. I'm the host then. All right. So let's see. Does somebody have a link to the LMD Go stuff that we were talking about last time?
It's probably still in the chat.
Okay.
Joshy.
Hey, good morning, everyone.
What's up, Joshy?
Morning.
Oh, hi, Josh.
Hey, Joshy, Isaac, Jay, Jeremy.
You.
What's up, Gary? Oh, we have someone new, too. Who's our Chinese friend?
Pretty quiet person, whoever it is.
How you know it's not Korean, bro?
It's me. I'm on twice. It's a decoy. JK. How's it going, everybody?
Again.
Good, good.
Oh, great.
Couldn't sleep last night, so I was doing some research on K-frames.
Oh, yeah?
Yeah, I even hit up Isaac about it. I didn't know that is what pretty much you make or use to create the semantics of different programming languages, which I thought was pretty cool.
Yeah, nice, dude. Good. All right, well, I wondered if you guys want to pick up, I think, Jeremy, it was you that posted a question about the bitwise LMD stuff we talked about last week, so I thought maybe we could do an example of that stuff.
Sure, that works.
All right.
Yeah, I also hope that we can get back to Hashgraph at some point. It spends a lot of time.
Oh, you did? Oh, wonderful.
Yeah. So I think I can honestly explain it at this point.
Oh, that's great. Should we just decide that like at 10:30 we'll shift gears even if we're not like all the way through the Casper stuff?
Yeah, sure, whatever works.
I would also like to do some Hashgraph. What do you guys think?
Yeah, I'm also
Down.
Nice. Okay, can you see my screen?
Yep.
So I started to put together this this diagram. Basically, I was thinking like we should go through an example of a live network using the notation that we've always used and are familiar with, and try to construct basically the same or at least like qualitatively similar example like this one that Vitalik has that we were using as our example last week. So I took the main points to be like this one chain that's kind of forming on its own, a basically normal chain here with maybe a couple little probably accidental forks. And so I tried to recreate that. So 4 validators, they're weighted 3, 4, 5, and 6. Common Genesis block that's under all of them. And then they just started making blocks. And so this was the kind of diagram we've always done since we were doing like even binary consensus, just showing the justifications in Casper. So I wanted to just make sure that it is actually valid, first of all, because I just sketched it out in the last couple minutes.
So
And
all
this
of them.
is just for 3 bits. Or
Yeah, oh yeah, right. So the 3 bits are my best attempt at generating randomness out of my brain, but they basically just represent like, pretend that's this block's hash. So we're going to use a hashing algorithm that gives us 3 bits output. And then we'll use that later when we sketch up the virtual tree.
And then B5 has the same hash as B2.
Oh, yep, when we've got a collision, I guess. So that's interesting because with 3 bits, we are only going to get 8 unique hashes and we might want that many blocks.
Yeah,
but I'm a little bit curious to just, if it really kind of messes it up, maybe we'll just add a bit to break that, but it might not matter. Oh, they are directly extending one another, so maybe it will matter. I think we should just change it, and we should change it. Oops.
Yeah, I mean, it depends. I kind of forget the algorithm, but if you, if it's like a concatenation, like each time there's a new block, it's concatenated on the Merkle tree or whatever it was.
Yeah.
Yeah.
So I was thinking like if 2 blocks collide hash-wise that are not near each other in the blockchain, it probably is not a problem. But with B5 coming straight off of B2, who knows? Okay, so maybe the one thing that we could add here is like one more block from Dave down here. So maybe we'll just call that like B7 and 0, 0, 0. I haven't done that yet. And then so like if we assume Dave is trying to just have his own blockchain over on the side, then the question was always like, is there anything else that we could let him see here so that he would still build off the right place?
Hey,
'Cause,
Dave's
like,
the one that's trying to be malicious, right?
yeah, Dave's trying to have his own blockchain that just runs down the side that doesn't acknowledge any of Alice or Bob's transactions or Claire's, unless he's fine to acknowledge them as long as it wouldn't make him build his block somewhere other than off of his previous block. So let's see, what if we draw this in? Is he now justified building where he did? Because now he would want to build his block off of Claire's instead of directly off of his own. So I think he maybe can't do those lines, that justification.
Yeah. You would want to build off of Bob, right? That'd be the.
That would be the honest place to build would be down here off of B6, off of Bob. Yeah. But if he's like, if he's basically being like this guy up here, then he's not wanting his blocks to be building off of the other chain.
Gotcha.
Yeah. So, okay, well, I think that's probably valid. And so then the next thing we have to do is draw up the diagram that actually shows the blockchain, because this is justifications here. So it shows like everything you've seen, regardless of whether you're going to build on it or whether it's even valid. And so then next we have to do the chain. So that we'll just call that like blockchain view. And so then we've got Genesis. So this one hopefully will look a lot like Vitalik's did. So that's Genesis. And then we've got, off of that, we've got B1. And it's a 110. So then, okay, so now we have to ask ourselves, where does B2 go, given its justifications there? Where do we build it onto the actual blockchain? So we know that when Bob created this block B2, he had seen the Genesis block and Alice's B1. So then, like, what's its parent blockchain-wise?
Just be stemming from B1?
Yeah. Exactly. So we can put B2. And that was a 101. And that one comes from here. Oh, okay. And then, so B3, that one's over here. So where's that go?
From Genesis directly?
Yeah, totally. B3, 0, 0. That goes back to Genesis directly. All right, B4 is Claire's. Ooh, so now we have an actual interesting choice, right? Claire has 3 justifications. B2, B3 are both options to build off of.
Mm-hmm. So I think B4 can build off of B3, but then when B5 comes, oh wait, no, never mind.
But Dave has more weight, so.
Okay, so Dave has weight 6, Bob has weight 4. Yep. But what's the cumulative weight behind B2 so far? Because Alice is also supporting that fork from Genesis.
Oh yeah, that's true.
So, because when we look down here, we have to say when we fork off from Genesis, we either go left or right, and supporting the chain on the left, we have 7, weight of 7. That way. Okay, so I think Claire builds off of here. Oh my goodness. That's okay. Listen, less of a blockchain now. But okay, so B5 comes in. Definitely B5 is going to build right off of B2. That's a 1 0 0. I'm just going to build off of here. Okay, that looks good. B6. So B6 sees this thing that's all the way back here, sees Dave's B3, but you know, there's a lot more weight over on the left so far. So B6. And it was a 0 1 1. All right, and then
So
finally,
question
yeah,
on what you just did. Can you scroll up a little bit?
yeah, totally.
So would be since it's all obviously it's direct parent of B2, B5, and also B3, would it technically go with oh wait, never mind, I didn't see B4. Never mind. Didn't see that one.
Yeah. So it's actually a descendant of B2, B5, and B3.
Mm-hmm.
Yeah. Okay, cool. And then so we've got this last one down here that we'll put in B7, and its hash was all zeros. And it just goes off of here. All right, so there's our regular old blockchain. Looks pretty good. We've got one main chain that goes G, B1, B2, B5, B6, one little probably accidental fork B4, and this probably malicious chain on the right, B3 and B7. So according to regular old Ghost, like we can actually write in our scores here and go through the forking at each point. So that would be like, we'd have 3 because only Alice was on that one, and then 7. Oh no, sorry, I'm doing that wrong. We have to do this from the leaves, I think. So 7, 5, 12. Oh no, so 12 for all the children of B2. Oh yeah, that's it, because Bob's, we can't add another 4 weights for Bob because we already have Bob's latest message down here and only latest messages count. 12, so same here, just 12. And then Dave was 6, 6, 18. Okay. So that's our.
Josh, can you explain why is 12 on V2?
Yeah. So the algorithm in general is you add up the weight of all the children and then the weight of this block. And so the weight of all the children is 7 and 5. That adds to 12. And the weight associated with B2 itself is 0 because you're only associating weight with latest messages. So in our Casper diagram, these were our latest messages. That's Alice's, Bob's, Claire's, and Dave's. And so down here, those fall 1, 2, 3, 4. So since B2 isn't circled, since it's nobody's latest message, it doesn't add any weight of its own.
Oh, you're counting B4.
Yeah, counting B4, yes, because B4 also supports B2.
Oh, I see.
Yeah. Okay, cool.
Okay, thanks.
Yeah, you're welcome. That's a great question. One thing I'm just now realizing is that this is already a binary tree, and Vitalik's thing is cool, supposedly, because it breaks bigger, more dense trees into binary trees. I'm curious if there's another way, if there's a way we can get something else branching off of B2 so we could actually see that. Cleared it already. I guess we could make Bob switch to honest, or Dave switch to honest at the end. What do you think about that?
Yeah, that can work. Where you only just sees B2.
Make B7 CB2 or a new block.
Oh, yeah. What if we make B7 CB2? Oh, that's fine. Oh, that actually would be really great. Yeah, let's do that. So he's a little less malicious here than he was in Vitalik's thing. Oh, we still need that too. Oh, yeah, right. Why can't I delete this one?
Yeah.
Why can't you delete that one?
It must point to the block that he created before.
Yeah, it's an equivocation if he doesn't see his own block.
Yeah.
Yeah, okay. This is the one where I can delete the pointer to B3. All right, so that's good. That's a nice, normal chain. It has a couple little forks. One of them happens to be a three-way fork, and so we're going to use Vitalik's method to split that back into a binary tree. Yeah, so now we can do like, I think he called this the virtual tree.
Yeah, that's right. And we split it up by the bits in the hash, right?
Yeah, exactly.
Cool.
So let's see here. We want our Genesis block first, definitely. And I think the deal is then after every block, we just automatically, without even having to think about it, draw in this. I'm going to need to save some space here, actually. This virtual tree. Okay, and ours, that one's done now, and the reason I went 3 layers deep is because we're using a 3-bit hash function. So in Vitalik's, he's using a 256-bit hash function, so there'd actually be 256 layers here, 2 to the 256 leaf nodes, and so, you know, basically no collisions. Let's just make sure that's correct. Oh, I wanted to make sure he has that set up the same way. Doesn't he say somewhere? Oh, yeah, right. Start with some block H and let C1 to be in the children. Yeah, okay, I think that'll work. Oh, maybe we can do what he did here and not explicitly draw out every branch of that tree. Where was I going here? All right, so we got to add, Genesis has 2 children now, B1 and B3. So where in the virtual tree does B1 go? Well, its hash is 110, and 1 means go to the right. 0 means go to the left. So we'll put B1 right there. And then we have a 100 for B3. Boom. All right, so we've got those both in. That looks good. So now we can put in B2. So B2 extends B1. So I'm going to not draw the tree explicitly again. Let's see. 101. So that means I want to go right, left, right. And all those other pink parts are just not shown, but there's just as many pink ones as there are blue ones. You know what I mean? Like they're still coming in over here and everywhere. Okay. So then we've got B5, I guess we can do next. It's a 100 and it builds off of B2. So here's a 1 left 0. Then we've got also B4 in the 001 position. So that's a 001. And then we've got B7 in the all 0 position. Oops. Yeah. Okay, cool. And so again, there's lots more tree down here. It just doesn't happen to have any leaves at those points, so we don't need to draw it. And then, okay, so B6 extends B5 in the 011 position. 011.
That's right. So yeah, our virtual trees are like humongous, right? Because
yeah, that thing's ginormous and sparse. Yeah. Most positions don't have anything.
Right. Well, right. Yeah, which we're demonstrating by even only drawing like a couple branches in it.
Yeah. Okay, and so what's the beauty of having done all of that? The beauty is we used to have B2 here that had 3 children, B5, B4, and B7. And that's not the case anymore. B2 now only has, because of this virtual tree, it's become a binary tree now. So the question that we got, now that we have this all drawn out in its entirety, I think maybe we can answer what I felt like I was stuck on last week, was this formula
The agreeing formula.
Yeah. Or what it says, to determine if a block is valid,
Right.
we now need only verify one property, and it's the property that there's no virtual height h where this agreeing of h plus 1 is less than agreeing with h minus at h. Yeah, shoot.
Did you figure out what the at h thing actually meant?
Set
of validators that agree up to exactly h of those latest signed message. Okay.
And whose latest signed message is of a block at exactly that height.
Can you say your schema what is the agreeing point in this virtual tree?
In the one we drew?
Yeah.
Yeah, the agreeing. Well, so agreeing is parametric in a point in the tree, or a height in the tree.
And it's going to tell you how many validators agree up to that virtual height, right?
Yeah, yeah. So, go ahead.
How many validators whose latest message agrees up to the virtual height, specifically latest message, of course.
Yeah. Okay. So let's look at that, I guess.
Yeah. Yeah. Let's just do an at h calculation for some virtual height. Maybe that would help.
Yeah. Do you want to do agreeing first or at first?
Let's do agreeing. I still kind of don't get that one.
Yeah. Let's do agreeing first.
Okay. So agreeing of 10.
Yeah.
So Genesis is 0. Oh, 10 might be too big, but we can go 1, 2, 3, 4. Oh, and there's an easy way to count them because they're multiples of 3, right? So every time you get to a real block, we can go 0, 3, 6, 9. So 10 works though. I guess 10 is this point. So then we have to say how many validators are agreeing up to this point.
Yeah.
And it looks like, I was going to say it looks like 1. Oh yeah. I didn't know if those guys, they're just not even up to that point.
Oh, no, agreeing up to this point. So
anything that you can trace from this path back to Genesis. So like B5,
is it
B2,
only
B1.
one?
But we're only scoring latest messages here, so these are our candidates.
Well, and B5 agrees up to 9, right? Height 9, but not height 10.
Another thing to notice though is B5 is in the chain of B6, I guess. Oh, B6 doesn't. We just chose a point in the tree. Oh yeah, so maybe it's just B5.
Oh, I thought it was just B6 that agrees up to this height. Yeah. Yeah, latest message agrees up to this virtual height. Maybe we should do a smaller height. That would be more interesting.
Okay, yeah, that's a good idea.
Let's do like I don't know, 4 or something.
Yeah. All right, agreeing of 4. So this is 4.
Yeah.
And really, this should go all the way across the full, I guess, something like that.
Yeah, yeah.
So, okay, so now I'm starting to think we still look at these latest messages that we see all the way down at the bottom here, and we just say, like, how many of these converge? They're all on this same pink path when we cross the line 4, so I think that means all of them.
Yeah. Yeah, basically all of them built off of B1, and that's kind of what we're looking at right here.
Yeah. Okay, so then the question is, what is the answer here? Is it 4 for 4 validators, or do I sum their weight? I feel like I should sum their weight.
Oh, I thought probably sum the weight, because I think he was treating them all as, like weight 1.
Yeah, okay, right. So what did that turn out to be in our case? We had,
what are the weights?
18. All right, so let's try again now.
Why are you saying exactly that height? What does it mean to exactly that height?
I think exactly came later, didn't it? Yeah, for agreeing it's up to.
But later,
Later, yeah.
Yeah,
it
for
says,
the at thing is exactly that height.
whose latest signed message is of a block at exactly that height.
Yeah.
The set of validators that agree up to exactly H
Up to.
and whose latest signed message of a block is at exactly.
Oh, interesting. So is at 4 going to be 0?
I think so. I think at means they agree up to exactly H.
Yeah.
So agreeing up to exactly H makes me think that if you trace their main chain from Genesis, you'll get H steps where they're exactly the same, and then the H plus first step is where they diverge.
Right. Yeah, that makes sense.
And whose latest signed message of a block is at exactly that height. So I guess that means like set of validators that agree up to exactly H and whose latest signed messages. I'm not totally sure.
Yeah, it seems like this at calculation might only be interesting at heights where there are actual latest messages.
Yeah. Okay, so I wonder, maybe we should be able to see these at the same time. I don't know. Oh, that's not what I wanted. Sorry. Cancel. Okay.
Oh, you're doing great.
So agreeing of 10.
Yeah.
So it almost sees like only B6 can go here because
Let's
only
do agreeing at 9 maybe then, and we'll have an interesting
okay.
at calculation.
Yeah, that's a good idea. Agreeing at 9. All right. So that's whoops. Oh, goodness gracious. That's exactly here that we're talking about.
Perfect. Yep.
Yeah. So, oh, well, wow. Well, none of them are agreeing at that. Oh, no, that's not true. B5 and B6 are agreeing at that point.
B5 and B6. Yeah, B5 and B6. Right.
All right. And so then that's Alice and Bob. Their weights were 3 and 4. So I guess we're going to say that's 7, right? Okay, so yeah, I agree. Maybe now we can try an at 9.
Mm-hmm.
And then we should switch to hash graph.
Yeah.
Okay, at is the set of validators. So we're not looking for a weight or a how many anymore. We're actually looking for the set of validators that agree up to exactly 9.
Wait, what? How are we going to subtract set of validators from a number?
Yeah, that doesn't make sense.
He's got to mean the number of validators in the set of validators that agree.
Yeah.
All right.
Okay.
Well,
so in our case, it's going to be a combined weight again then. Okay.
Yeah, I think so.
They agree up to exactly H. Well, that first criteria, that is still B5 and B6, right? Or Alice and Bob here. They agree up to 9, but then they diverge because Alice is still because Alice is still at 9 and Bob is later.
Yeah, right.
Okay. So here was the definition. So I think at is just going to be Bob. So I think it's saying like everyone who agrees up to this point, minus the ones who have, not diverged at all. So like you can imagine if we had some other block that was like here, BX, we'll call it. So B5, B6, and BX all agree up to 9. But B5 is the only one that's at 9 because BX and B6 have both moved on past 9.
So is it only possible to have at most, I don't know, can at H be at most 1?
Yeah, I feel like that would be the case because if it were on another branch, then it wouldn't agree.
Yeah.
Right, exactly. You can't have two blocks occupying a node, right? Because then they'd have to have the same hash,
The same parent and the same hash.
the same parent and the same hash. Okay. Yeah, and even if you built an empty block, that shouldn't be the case, but
Yeah.
okay.
Okay, so that seems right. Part of me wants to say, like, it seems now that we're talking about this a little bit, it seems really intuitive to say like B4 is at 9. I would love to say that. But over here, I think
right.
you're saying like part of at means they have to be agreeing already.
Right. Yeah, it almost seems a little bit weird because like if we had another block that was being built off of those two that we didn't consider in the at 9 thing, then like can you go back to the diagram that you're drawing? Yeah, so if we had another block building off of say like B4 or something, yeah, I'm just wondering how we would do the calculation at that point.
Yeah. Oh, well, let's give this mysterious person a weight. Let's just say they're like, I don't know, 5.
Yes. Yeah.
So we got to decide like what. I think we first have to decide. Oh, yeah. Wow. Oh, well, this is always done in someone's local view, actually.
Okay. Always done someone's local view. That makes sense.
So we could just think of this as like, we're Bob. We have Bob's local view. We made B6 recently, and this is what we've seen otherwise.
Right. Right.
Okay.
Right. So yeah. So Bob's just seeing who agrees with him, basically, right?
Yeah.
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 Okay.
And so
That
I
makes
guess Bob would say, "Oh yeah. Oh, that's a good point. Who agrees with him?" Yeah. That's a great point.
But that's interesting then, because then validity of a block is like a local property.
Oh wow. Yeah, because this is how well, we haven't actually looked at the condition yet, right? We just figured out how to calculate the subparts so far.
Yeah, I guess. So.
Yeah. Okay. So maybe next time we'll make this calculation for a few blocks from one person's view and the next person's view, and see if they like if there's any case where one person finds a block valid and another one finds it invalid.
Yeah.
Because I agree. That seems like something we don't want.
Yeah.
Either valid or not.
Right. Right.
So.
Cool.
All right, cool. I think that's a good amount of Casper to today. Jay, do you want to do some hash graph?
Yeah, definitely.
Nice.
You want me to pull it up?
Yeah.
Okay, so I also found this YouTube video by Lehman Baird. It's 1 hour long, and it basically goes through the paper. It doesn't talk about forking, but it explains the whole consensus algorithm. I'll share that in the chat. We're done.
I think I watched that same one. I watched an hour video by Lehman Baird. It was awesome.
Okay, yeah. I mean, that pretty much explains like, I think he has the whole algorithm boiled down to like 3 different sub-algorithms here at the bottom, 3 different procedures, and they're really tough to understand. Another interesting thing I found in this paper is at the very bottom, he defines everything in functional terms.
Oh, cool.
So all the like procedures that you need to determine like if a block is famous or a witness or an ancestor, any of that, which is pretty useful. I don't remember exactly where we were.
I think we left off somewhere around this diagram, but I don't remember exactly what we had talked about. I think what I remember is like the heart of it is every once in a while you call up a random other validator and tell them everything you know that they don't already know, or something.
Yeah, yeah. So yeah, I mean, wish I had a thing to write on that'd make this easier. But basically, he decided to partition everything into rounds. So there's this concept of a round, and it's really only to like optimize the search space. so that you only have to search for a node within a round. The ordering comes from, there's like hierarchies of ordering. So first you order an event by the round it's in. So if an event is in round R+1, then it's, higher up than round R. And then events within one round are ordered by the timestamp. So obviously you can make a timestamp. So the whole point of like finding a witness and strongly seeing is all about how you can calculate the timestamp.
Interesting. So it's like a lexicographical ordering.
Yeah, this timestamp is not like a word clock, right?
It's kind of like that. I mean, it's like a consensus clock. So yeah, once you understand that part, you can work backwards, and then you can see how the consensus algorithm works. Basically, it's just that each round at the beginning has a witness, and so these are the genesis events down here. Each one of these is a member, and so genesis events are by default witnesses. They're the first block in the first round. And in order to become a witness in the future, I think you have to strongly see 2/3 of the members, or you have to strongly see some of them, two-thirds of the members, 2/3 of the events from all members. Let's go get the exact definition.
You said events. This what does it mean to see gossip about gossip, or
like what is an event?
yeah?
I mean, an event is just yeah, exactly. It's when you receive gossip from someone, or you can create your own event by sending gossip to someone else. So one event can strongly see another if it can see more than 2/3 of the creators, each of which sees Y.
Oh, so okay, right. So C above that, I think makes a lot of sense, right? If Y is an ancestor of X, but no fork of Y is an ancestor of X. Oh, maybe I don't get that as much. But it sounds like strongly seeing is like whatever notion of seeing they have. Strongly seeing means like I can see a whole bunch of people seeing Y. There's like it's 2 hops away, and there's a whole bunch of different ways I can make those 2 hops, a whole bunch of intermediates.
Yeah, exactly. And it doesn't even have to necessarily be different ways, as long as you just somehow traverse through 2/3 of all the members in the graph.
Oh.
Can we say that this means that this is like a final view? It will not change.
Yeah. There's a concept of finality. I don't know if strongly seeing is where you get finality. I think it's with like famous witnesses. I'm not totally clear on that.
Okay.
But as soon as you get an event, you can immediately determine its round, and that will never change, even in the case of a fork.
So
yeah,
if
then,
you get an event, you can immediately determine its round. Okay, that's cool.
yeah.
How does that work?
Because it just builds off of its round is either the greatest round of one of its 2 parents, or it's R+1 if it turns out to be a witness, and you determine if it's a witness if the event has a greater created round. Okay, that's an awful definition. Yeah, that's what I mean. Some of these are like extremely recursive and hard to.
Yeah. Okay.
Yeah. Somewhere up here. So he has some concept of a witness. First event they create is called a witness.
For any given member. Oh, okay. Okay, so members are like the validators, right?
Yeah, exactly.
Okay, and so they're over here creating all these events. They create an event every time someone else calls them, right? That's when I make an event, when I receive a call.
Mm-hmm.
And whenever there's some means by which I can determine which round I'm going to create the thing in, and if it's the first time I've created one this round, then it becomes a witness.
Yeah, exactly.
So if we have like n members validating this thing, then there are going to be n witnesses every round, one from each member.
Yeah, as long as you participate in that round.
Oh yeah, less than or equal to n.
So there's still got to be a good definition of witness somewhere. Oh yeah, I think this right here is describing what a witness is, or is it strongly seeing?
Illustration of strongly seeing, okay. In each hash graph, the yellow event at the top can strongly see one of the orange events on the bottom row. There are 5 members, which is why there's 5 vertical lines, I think. So the last integer greater than 2n/3 is 4. Okay. And, so that's how many of the 5 validators we have to see 4 of these validators seeing the orange event in order to say yellow strongly sees it.
I think that's or sorry, say that again.
So there's 5 members here, and 2/3 of 5 is 4.
Yeah.
So in order to say yellow strongly sees orange, there has to be a route from yellow through at least, or combinations of routes from yellow through at least 4 of the 5 validators to orange.
Yeah, exactly. And then there's another concept that I think the definition of a witness is that it can strongly see, so through 2n/3 different members, it can strongly see 2n/3 witnesses from the previous round. So because it can see 4 different witnesses here, it is now a witness itself.
Okay.
So yellow becomes the first.
Wait, no. That's what famous is, right? If you can see 4 different ones or something, or
yeah, famous comes later.
Okay.
Famous is another concept.
Okay.
Yeah.
Each of the other. Okay, so like that one on the left, yellow sees orange through actually all 5 of the members, and that's okay because it has to be at least 2/3, and all of them is at least 2/3.
Yeah, exactly. So it's like this concept of 2/3 twice. So once for strongly seeing the specific witness, and then once for seeing 2/3 of witnesses. Because there's a strongly seeing path for 4 different witnesses, this guy becomes the first in the second round, the first event in the second round. And now when a new event occurs that's an ancestor of this witness, then it becomes part of round R+1.
Oh, so this makes sense. So it's possible, like, it's not like we're all advancing rounds simultaneously. Like I could have make an event that, meets these criteria and thus moves on to round R+1, whereas like someone else might still be in round R or even round R-1 or ahead of me or something, just based on what they're seeing.
Yeah, like if they haven't synced to this member yet, like if an event goes to here from here, then that would still be in round R.
Yeah. Okay, that's cool. Yeah. So that's how we know. So that's the algorithm we run when we create an event or when we hear of one, to know what round it's in, basically.
Yeah.
Wait, is that right? So how did we get like all those 4 orange ones at the bottom? Those are all assumed to be in round R, I guess.
Yeah, these are the genesis events, so they're all witnesses.
Okay, I see. So every member makes a Genesis event. That's just like how this thing starts, right?
Mhm, yeah.
Okay, cool.
Yeah, I guess that's kind of interesting when it comes later. You know, like, I mean, I guess it doesn't matter exactly when, but like if you create a Genesis event a lot later down and you, I don't know how that would affect the round creation.
Yeah.
But yeah, so from here, once you can determine rounds, then there's the concept of a famous witness. And famous witnesses are how you calculate the timestamp of a block with finality. So a famous witness, we'll have to look up the exact definition again. I don't want to butcher it. So for each witness, it decides whether it is famous. So a witness is famous if many of the witnesses in the next round can see it. And it is not famous if many can't. So yeah, that's
Okay.
a pretty simple concept.
Runs an election for each witness to determine if it's famous.
So every witness will be becoming a famous, right?
Yeah.
Eventually.
It should eventually, yeah.
No, not eventually, because it has to be in the next round.
Well,
I mean on the correct chain.
it can happen in any future round. Because if in the next round, say there's only like a few witnesses, or I can't think of a good example exactly, but it doesn't have to be the next round. It can be any round. When eventually enough witnesses see you, 2/3.
I lost the definition. Where was that real quick?
I think it's in that last paragraph.
Oh yeah, nice. A witness is famous if many of the witnesses in the next round can see it, and it's not famous if many can't. The Byzantine Agreement Protocol runs an election for each witness to determine if it's famous. For a witness X in round R, each witness in round R+1 will vote that X is famous. Yeah, so I think if you get to round R+2 and you're not famous yet, then you're never going to be famous.
Oh.
Why do you think that?
Because it says, I lost it again. Somewhere in there it says for a witness to be famous.
For a witness to be famous.
Oh, there. Oh, yeah. Yeah, so it says if many of the witnesses in the next round can see it, and it's not famous if many can't.
Yeah, I see that, but
Yeah, you're okay, but your impression from other places is that it can be.
But maybe you can receive. Okay, can you receive some messages later that from? Can you receive these messages from this like a next round in some later point in time?
Oh, a couple sentences down, it says that it continues for as many rounds as necessary. Because it says if more than 2n/3 agree on whether it is famous, then the community has decided and the election is over. If the vote is more balanced, then it continues for as many rounds as necessary, with each witness in a normal round voting according to the majority of the witnesses that it can strongly see in the previous round.
Mm.
Oh.
Yes. So when a witness votes to determine
right.
whether another witness is not famous or is famous, if they can't determine, then they just vote with the majority of what they can see.
Yeah.
The witnesses that votes they could see.
Yeah, it looks like if it's over, 2/3 or whatever, then it's like a definite yes, and if it's less than some threshold, then it's a definite no, and if it falls into that intermediate range, then it continues on into the next round, I guess.
That makes sense.
What this member do when he decide is it this witness famous or not? It sends some message to others and say, okay, I found out that this is like a famous witness or not.
It's all a virtual voting. So really, you're just like looking at any specific witness on your like local machine in your local copy and seeing if it can see that witness, and if it can determine that it's famous by the majority of witnesses seeing it, then it would vote yes. Otherwise, whatever case it is.
And
So
after you decide this locally, then you send this information to others, right?
No, because everybody should be able to compute the same thing locally, as long as they've seen your witness. And if they haven't, then that's when you would have to move into the next round and keep voting. But you don't actually send anything specific. You really just keep gossiping about gossip as you were.
Right. So like, I think Tomislav, if you have enough information locally to conclude that a witness is famous, then you don't call me up specifically to tell me the witness is famous, but you call me up and tell me everything you know, just like you always did. And therefore, I now also have the information that you had, so I can also conclude that it's famous.
Yeah.
Because you are using this information that I sent you.
Right.
Exactly.
What I decided.
Yeah. So
Well,
now you can
yeah, but you're not so much sending me the like, hey, it's been decided that this is famous. You're just sending me the like, here's a bunch of shit that I knew, and then I'll also, in the same way that you concluded it was famous, I'll also conclude that it was famous.
Yeah.
And in a sense, this is the same as justification in Casper. Right.
Yeah, seems like it.
And did you listen to the Greg explanation last Casper stand-up?
Yeah, I watched that video. What was it again?
He was talking about this like a path that you can find out from these messages from all the validators.
Oh.
And he was saying that you don't want, you can't build something that have word clock. You can just say, you can just have this, he didn't say virtual, like virtual time. You can say what events, what are the order of events, but you cannot say like the real time.
Oh, yeah.
This is why I'm asking if the hash graph has this some kind of.
Yeah, so we're still getting to the concept of how they do order in real time with timestamps, but they get it from the order, like the topological order of the graph. So it's once you have a famous event, and maybe they have a graph somewhere that shows it now. So yeah, just to be clear, like in this example of famous, like these witnesses down here are not yet famous because 2/3 witnesses in some future round can't see them yet. But if a couple more events occurred in the next round, all of which would be witnesses, then these events would become famous because all of these would ideally be connected to this first witness, and therefore I could see all of these witnesses at the first round. That makes sense. Basically, all these witnesses at the bottom would become seen by 2/3 of the witnesses up here after a few more events.
Yeah.
So, is there any relation between the concepts of like being famous in Hashgraph and like being in a particular clique in like Casper or something? Because it's almost like yeah, I don't know. I feel like there's some sort of connection. I can't really put my finger on it exactly because it's almost like you know that. Yeah, I'm not quite sure how to say it yet. I don't fully understand.
So I have a quick question on this. If I can speak for a quick second in terms of the hash graph. So if it typically still goes off of what everyone sees, how would it like do if everyone wanted to collude? So we have, let's just say, 10 people, then 6 of the 10 colludes to where they all see the false messages. So the next person who tries to be famous or sees the history disagrees on it. Like, is there like any set protocol for that?
Well, so I mean, you only have consensus for 2/3 majority. So if 2/3, 6 out of 10, that's like at the 2/3 mark.
Yeah. Okay. So yeah. So what's our member? This is like all members are created equal here, right? Like one member, one vote.
Yeah.
Okay.
I think so.
And so in order to kick this thing off, you need to agree on a set of members, a fixed set of members now and forever, right?
Yeah, that kind of goes back to the question of like what happens later if a witness joins. I'm not sure.
They must have some notion of like validator bonding or something like that.
Yeah. The members can rotate?
I mean, would it be realistic if they couldn't?
Now, down at the bottom, they have a section on proof of stake. I think it's kind of like an add-on that they do at the end.
Okay. Okay. Cool.
My understanding was that everybody can be like a validator or member.
Yeah. Yeah, it's just, what's the like civil mechanism to avoid an attack.
So where do we put in transactions here? If we're there's something that we're coming to consensus over, ideally, or I would think. So
yeah. So let me show you this.
Yeah.
So I was working on an implementation in Rust.
Oh, cool.
Yeah. And so this is an event right here. It's just an enum. It's either Genesis or an update. And an update has a creator, a self-parent, another parent, and then a list of transactions.
Okay.
So it's basically just a payload that you can pass in whenever you want.
Yeah, okay.
So they're just expressed.
So in this case, so I create one of these update events every time some other validator calls me, right? And when someone calls me, that's when I have the opportunity to inject my transactions then.
Yeah, okay, so that's a good question. You can see here that you can create an event without ever receiving first.
Oh, cool. Okay, so you can do ones that are just like, hey, I just felt like making one, Yeah. No one called me, but okay, cool.
Yeah, exactly. That's what makes it really confusing from like an implementation standpoint, because it's a graph that like is somewhat cyclic. It can have, one or two parents, but it's hard to tell which, and there's no like real way to traverse directly. Like if you wanted to traverse by other parents, then all of a sudden this would become hidden.
Yeah.
In that version of the graph.
Yeah, right.
Yeah, so okay, we're at the last concepts now. Once you have enough famous witnesses, then you can determine the timestamp of an event within a round as the timestamp of a self-parent or self-ancestor of a famous witness that first saw that event. So if we could pretend that this yellow one is a famous witness, and we're trying to determine the timestamp of this event right here, then this would be a self-parent, this would be a self-ancestor of the famous witness, and so this timestamp would represent the first time that this member saw this event that we're trying to determine.
Okay.
So you do that for all the famous witnesses, and then you take the median of all the timestamps that each of them saw that event at.
Okay.
And that's the timestamp.
Okay. So we're trying to find the timestamp of that red one, that little red one. And there's some timestamp in that actual event itself, but that's not ultimately going to matter. What's going to matter is the timestamp of the first famous witness from each of the 5 validators that sees this red event that we're talking about.
Yeah, and they have a word for it. It's received time.
Oh, okay. Okay, cool.
But yeah, I mean, that's really the last concept. Once you have that, you have a total ordering.
Oh, wait. Okay, so that gives us a total ordering?
Yeah.
So okay, let's look at figure B there, I guess then. And like I'm just gonna choose to like the far left red dot and the far right white dot. Which of those happened first? Yeah, those are the two.
So, I mean, so we don't really have any famous witnesses, so it's hard to say exactly. But
Oh yeah, okay.
But if this were a famous witness, then it would see this event first. I guess like that. I guess this, yeah, itself is the first event that it has seen this red dot, and then this one. So it would, yeah, depend on this timestamp.
Right. Okay. Yeah, that's interesting. Wow. So like the big thing with RChain was like stop making a total ordering. That's wasting all of our time. But it seems like here we still got a total ordering.
But how can we trust these timestamps? We can say whatever we want for timestamp, right?
Yeah.
Well, yeah. So I mean, I guess I don't know how the timestamps are determined for Genesis blocks. And yeah, that's kind of like the Big Bang scenario. We don't know if you can even add validators or not. But if you can assume that these are like valid timestamps, then like you can deduce any timestamp from here based on that.
But I mean, when I'm sending this gossip message, I can change the timestamp a little and lie about like exact timestamp.
Yeah, I mean, there is wiggle room to lie. Like basically this event right here could lie and say it was a little farther back, as long as it doesn't go too far back that another transaction says, no, I've seen one since then. And it can also move up toward this event. But I mean, the timestamp doesn't matter, really, the order matters. So it can never cross behind a different event or ahead of another event. It can only move within the range that it doesn't matter.
But,
yeah, go ahead.
But did you find out why the timestamp is actually needed? Because it's not exactly the time of event. It's more like a relative time. So I'm just interested why it's needed.
Yeah, I'm not sure.
Well, I mean, it sounds like it's what gives us the total ordering, right? Because we now have a way to calculate the timestamp of every event here, and then once we have that, then we can put an ordering over them.
Yeah, but why not just like assign like an increasing sequence number from like this event, like it's this one 2 events back and this one 2 events back.
Yeah, like within each round, just have like some ordering for all the events within the round, and then move on to the next one.
I'm wondering if this is the case, really.
Yeah.
To call this like a timestamp, but it's really just like a.
Maybe they found that they're like more or less equivalent, so they just figured the timestamp was easier to implement or something.
Yeah.
So, Jay, do you want to show us more of your code?
Yeah, I mean, I'm still working on it. I've changed it like 4 times now. Mostly because Rust it's tough to build graphs in Rust because you have multiple dependencies or multiple pointers to the same object if you build this in an object-oriented way. So you can see that each event itself parent links to another event. And the box just means basically like a pointer on the heap. And so I'm actually referencing it as a pointer to this box. And this is actually okay because basically the entire graph is immutable. It never will change, even in the case of a fork. So in the case of a fork, you still keep the fork, and that's basically just a reminder that that validator is not to be trusted. So it actually makes it safe because as soon as you throw immutability out the window, then you can have pointers and any of this, and you never have to worry about dangling pointers or anything changing under you. And so what I did is I kind of like broke up the immutable graph structure and then everything else that would be mutable. So here's the concept of a round. So you have a set of events in a round, and then you have a witness, which is a mutable part, because at the beginning, you don't know if an event is going to be a witness or not. Sorry, you don't know if it's going to be famous or not. And so what this does is it just is an event hash that points to, if it's none, then it's not a witness. And if
It's not famous, right? Oh, no, none means it's not a witness.
Yeah, yeah. And if it's some, then it's a Boolean. So it's basically kind of like a double.
Yeah.
Yeah. So, because you can't determine is famous for a while, and so that's why I put it into it. I didn't put like an is famous right here, because then all of a sudden the graph would be mutable. So.
Oh, yeah. Oh, I see what you're saying. So you can keep like the graph itself immutable, whereas like you can learn progressively whether a witness is famous and still mutate that.
Exactly, yeah. So the round structure can be a mutable structure that just contains an immutable graph.
Yeah, oh, nice.
Yeah. And then I built an iterator for the graph that kind of just makes it easier to do a lot of these concepts, like here's the ancestor and strongly seeing. Ancestor is easy. It's just iterate through all the children of X or any path from some event, and if the hashes are equal, then, or if the hash is equal to the event that we're looking for, then return true.
Nice.
The hash is like an object. So
What was that?
I'm asking that is it hash like an object hash of this object memory? Is that your hash function?
That would be the one that's supposed to be in hash graph. So whatever, like SHA-3 or signed message.
Oh, I see.
So how do you iterate over the events in a round? Like what's the ordering? How do you make sure you didn't miss any?
Yeah, so okay. Basically just yeah, so here's the hash string.
Oh, okay.
Yeah, so when you create the iterator right here, you push. So I have this method called push self parents, and it basically just runs down from one event and pushes all of that event's self parents. So now you have a list of just that self parents, and then on each next iteration of the iterator, then you run push self parents again on the current events, the next event's other parent.
Yeah.
So it's kind of like a diagonal traversal.
Yeah, right. So it basically takes like an event and then iterates over every event that is seen by, or I don't know if it's the hash graph sense of seen, but like every event that is further down in the graph.
Yeah, exactly. Yeah. It's definitely like not going to be the most efficient method. And I mean, you can do things like take until, but I'm sure that there's got to be a much better algorithm out there for like determining strongly seeing than doing like a depth first search.
Yeah, that's cool code, man. That's awesome. Is this one big Rust file and this is basically the whole algorithm?
Yeah, I'm going to split it up eventually. I've just changed things so much that I'm kind of leaving it together.
Yeah, nice. How long is it? A couple hundred lines?
260.
Not bad. Dude, that's cool. Wow.
Yeah. Well, I'll have it on GitHub, so you can share it.
Sweet. Nice.
Cool.
Okay. Well, I guess should we wrap consensus there then and talk RoCalc or similar things?
Yeah, man.
Yeah, sure.
All right.
Cool. Well, Jay, thanks for presenting today, man. That was super helpful.
Yeah, you did kind of made sense.
Yeah, totally, man.
Oh,
Yeah, very
definitely.
good. Yeah, that was awesome.
Yeah, I mean, I spent last week at a hackathon and we tried to implement the whole thing in one night. And then I was like, oh God, this is so
Whoa.
yeah.
Curious question. I'm not sure if you answered this or not, but what made you decide to go with Rust for it? Recording it up.
Just because I hate myself. No, I mean, it's an interesting challenge because usually my impulse when designing something is to do it in the object-oriented way. And
Yeah.
when you're designing a graph, it's really easy to create dangling pointers or some big mistake like that with all the dependencies. So I figured Rust would be a safe way to make sure I designed it right the first time.
Yeah, nice.
Wow, that's awesome.
Yeah, Rust would be my choice for Erlang.
Rust would be?
Yeah.
Oh, cool.
Are we going to stop recording now, or we're done with the cat?
Yeah, yeah. We'll stop and restart.